What's up, everyone? It's good to be with you again. Welcome to episode 13 of Ask Abhijit. Today, I answer your questions about astrophysics, space, and the universe. And as always, you guys have asked me a great deal of questions, very interesting questions. And I have picked a bunch of questions out of those, which hopefully represents a wide spectrum of topics that will cover the whole range of issues in astrophysics and cosmology and space and the universe. So let's get right into it with question number one. So Aditya asks, can gamma ray bursts and magnetars wipe out the entire life from the Earth? That's a good question. So let's first discuss what gamma ray bursts are. What are magnetars? So a magnetar it's a neutron star that has an extremely powerful magnetic field. What's a neutron star? A neutron star is the collapsed stellar core of a supergiant star that went supernova. And the parent star typically has a mass of about 10 to 25 solar masses, and the neutron star typically has a mass of about 1.4 solar masses and a radius of about 10 kilometers. So it's an extremely dense, extremely compact object. And a magnetar is a highly magnetized neutron star. It has an extremely powerful magnetic field, typically about 100 million times the strength of the most powerful man-made artificial magnet. So that's what a magnetar is. Now, are magnetars responsible for gamma ray bursts? Not really. Those are not the real progenitors of gamma ray bursts. So let's go into what is a gamma ray burst. A gamma ray burst gamma ray bursts are some of the most energetic events in the entire universe. So it's a very powerful flash of light, mostly gamma rays, and the luminosity, the amount of light that is emitted. So it emits in just about 10 seconds or so more light than the entire sun will emit during its entire lifetime. So that's how incredibly energetic a gamma ray burst is. So typically there are three different kinds of gamma ray bursts. Very short duration gamma ray bursts, typically of the order of milliseconds. Then there are medium to long duration gamma ray bursts from about a second to about 10 seconds to maybe 100 seconds. And then there are longer duration gamma ray bursts. So the ones we are talking about, the vast majority of gamma ray bursts, are these short duration to medium duration ones, about 10 seconds or so long, approximately 10 to 100 seconds, typically 10 seconds or so. So how are these gamma ray bursts formed? What is the origin? Typically, it's the supernova explosion of a supergiant star. So that's typically what gives rise to these gamma ray bursts that are of the order of 10 seconds long. And when a star like this goes supernova, it emits these beams of light. So let me show you what it looks like. So this is an artist's representation of a gamma ray burst. It is a star that has gone supernova, and it's emitting two beams of radiation in opposite directions. It's aligned along the axis of rotation of the star. So that's what it typically looks like. These are extremely energetic beams of radiation. It contains all kinds of radiation, but typically the most powerful, the most significant component is gamma rays. The explosion also gives off lots of neutrinos and things, but these two collimated beams of radiation are mostly composed of gamma rays. So let's go into what are gamma rays. So gamma rays are the most energetic form of electromagnetic radiation. It's a penetrating kind of electromagnetic radiation. A gamma ray typically has possibly millions of times more energy than visible light. And its wavelength is extremely short. So the consequence of this is that you cannot reflect gamma rays off mirrors. The wavelength is so short that it goes right through mirrors. It goes right through living tissue, and it can cause a great deal of radiation damage to living tissues, which is why these are extremely hazardous light rays. So these are invisible, obviously, and they can cause a lot of damage. Typically, you need to shield yourself from gamma rays using something like lead, which is very thick and which has a great amount of density. So gamma rays are on Earth emitted from various radiation processes, from the radioactive decay of atomic nuclei, etc. And that's what you find in nuclear reactors. So that's why you need all this radiation shielding. So it's very dangerous to human beings. It can cause damage to your DNA, to your bone marrow, to internal organs. So that's why it's very hazardous. So this event. So how was it discovered? So in the 1960s, the Americans sent up satellites in Earth orbit, and the purpose of the satellites, the Vela satellites, was to detect nuclear tests anywhere on the planet. So a nuclear test usually has a very typical signature. It's a double flash signature. It's a very powerful initial flash of light, then it is followed by a slower and gradually increasing afterglow of radiation. So it's a very interesting, very typical double flash event. So that's what these satellites, the Vela satellites, were designed to detect, and they were equipped with X-ray detectors, gamma ray detectors, and other such instruments. So what these satellites found was they found strange flashes of gamma rays, strange gamma ray bursts coming from outer space. And there was no explanation for that at the time. And this was a classified deal. These satellites were classified, their data was classified. So it was not revealed to the scientific world until the mid or early 1970s, by which time it was found that these events happen from time to time in outer space. Eventually, it was detected that these are extra galactic events. These events don't happen in the Milky Way. They occur very, very far away in far off galaxies. And their distribution is isotropic, which means it doesn't come from any particular direction in space. It's spread all over. So now we have a better understanding. The gamma ray bursts we are referring to, the short to medium duration ones, they originate in these supernova explosions of these supergiant stars. So there are two beams of light. So if the Earth were to come in the path of one of these beams, it could affect the Earth if the gamma ray burst was nearby, maybe within 1,000 light years or so, or maybe less. So if it is at a reasonable distance from the Earth, it can definitely cause some changes on the Earth. The first thing is, if a gamma ray burst were to hit the Earth straight on, one of the beams, then within seconds it will destroy a significant portion of the ozone layer of the Earth. So at least half of the ozone layer will be gone within seconds. And it will not affect the surface. It will not have an effect on the surface of the Earth directly or immediately, but it will wipe out significant portions of the ozone layer. And that will cause a great influx of ultraviolet radiation on the surface of the planet, which will have dangerous and bad effects on life on the Earth. And also the destruction of the ozone will also have a different effect in the chemistry of the atmosphere. It will react with nitrogen. It will create nitrous oxides and dioxides, which are gases that have a long-term cooling effect, because they produce a kind of smog that covers the planet. So you could have a kind of an induced winter, the kind of winter you have after an asteroid impact event, that sort of thing. So it will have long-term effects. It won't have immediate effects on life, but it could possibly and conceivably cause a mass extinction event of some type. So it is believed that some mass extinctions in the past may have possibly been triggered off by a gamma ray burst event. So that is the answer. It can possibly affect life on Earth, but most likely such a gamma ray burst would have to be directly aimed at the Earth, which would be it would be just bad luck if that would happen. And it would need to be somewhere within our own galaxy, because it needs to be close by for the intensity of the beam to be significant enough to cause all this damage. So yes, possibly it can. It definitely has the potential to cause significant damage to the Earth. I don't think it can wipe out the entire life of the Earth, but it can certainly trigger off an extinction event on some scale. So that's the answer. It's a good question. This is from Meenakshi. In a session, you explained about cosmic strings and that all galaxies might be connected through them, maybe from the supermassive black holes at the center. But as the universe expands and these galaxies go far away from us, will they still be attached to The strings, do the strings expand as well? Also, can one galaxy be connected to more than one galaxies at a time? And it was after a video. Okay. So what I referred to is cosmic strings, which are a kind of topological defect. Let's not go into what that is. It's essentially a defect in space-time itself. It's a wrinkle in space-time, so to say. So according to string theory, these cosmic strings, topological defects, could have been created in enormous quantities in the very initial moments after the Big Bang. So these are defects in the fabric of space-time itself. These are wrinkles in space-time. Let me illustrate what it means. So let's say you have a cosmic string. It's maybe 1 atomic diameter thick. It's very, very thin, very, very thin, but it is a wrinkle in space-time. So if you have a cosmic string this way, and you want to start from point A and go all the way around it and return to point A, then you will find that you have not traversed 360 degrees. You have traversed a distance that is less than 360 degrees, because this is a wrinkle in space-time itself. It warps and distorts space-time. So going around it, you will find that you have traversed less than 360 degrees, and still you have reached the initial point. So that's the kind of defect it is in space-time itself. And it is a warping of space-time, a wrinkle. And these effects also cause gravitation, because gravitation is the curvature of space-time. So cosmic strings are massive. They have mass, they have gravitational effects, they can cause gravitational lensing, they can split a star in two if we are looking at it through a cosmic string, etc. So that's the kind of effect a cosmic string has. Have we found any thus far? We have thus far not observed any evidence of cosmic strings, but it is a possibility. These may exist. And like I said, these may have been created in the very initial phase after the Big Bang. And as the universe expanded, these strings stretched out in all directions, and they would still be around. So these cosmic strings would probably be longer than the radius or diameter of the observable universe. It's possible, yes. And these are very tightly stretched strings. They are vibrating and causing gravitational effects if they exist. So that's what a cosmic string is. Now, what's believed by some people is that cosmic strings could basically be at the center of wormholes. So every cosmic string would have a wormhole around it, and these wormholes would remain open because of the presence of the cosmic string within. Typically, a wormhole is something that snaps shut because of the way space-time is. Space-time wants a wormhole, if it can be created, to immediately snap shut and pinch off. So it's very hard to have a wormhole that remains open, that you can actually traverse it. So that's the Einstein-Rosen bridge that snaps shut immediately, almost immediately. It wants to snap shut. So the main problem with wormholes is to create a traversable wormhole. And for that, you need something like negative mass or something, which will repel space-time and keep the wormhole open. So that sort of substance doesn't really exist as far as we know. But a solution could be these ancient topological defects called cosmic strings. Those could keep wormholes open. Now, the other thing is that some physicists believe that these supermassive black holes that are at the center of most galaxies, these could actually possibly be wormholes, portals to another dimension or to another region, not to another dimension, but to another region in space-time, maybe a far-off region. So it could connect two very distant regions of space-time, and you could traverse this wormhole and reach that other location almost in very little time. And if there are cosmic strings that are threaded through these wormholes, then maybe that's what keeps them open. So this is all hypothetical. We have no evidence of it, but theoretical physics does allow this sort of an eventuality. So that is essentially what I was referring to. If these supermassive black holes are actually wormholes. Now, can one galaxy be connected to more than one galaxy at a time? We don't know. It may be possible, it may not be possible. If it's a wormhole, it will definitely have at least one location to which it is connected. Can a wormhole connect to more than one place at a time? I'm not sure that is possible, but at least there's a one-to-one opening, one-to-one correspondence between one wormhole, between the opening and the exit of a wormhole. So that's in short about this question. It's an interesting question, but like I said, we have never actually observed. We don't have any observational evidence of cosmic strings. People have been looking for them, primarily via the gravitational lensing effects they would have, because mass basically warps mass. The presence of mass makes light travel in curves. So light is no longer able to go in a straight line. When you have mass, the path of light itself is curved. So that causes this effect called gravitational lensing, in which stars and galaxies are seen from the Earth as being distorted in shape because of the presence of some mass between us and that particular star or galaxy. So if a cosmic string is between us, directly between us and a star, then maybe we could see a star split in two for some time. So people have been trying to look for that, but thus far we have found no evidence. Maybe it means that these may be quite rare, or maybe few and far between, because the universe is expanded to such a great extent that this initial collection of cosmic strings has gone off in all directions. So maybe it's hard to observe. And as I say, it's very thin, and that could be another reason. So we don't know if they really exist, but according to string theory, these could exist, and these could have been formed in the early universe, and they could still be around. So that's the answer. Good question. Shreyas asks, why are all planets and stars round? Why not square or triangle or rectangle? It's a silly question, but I'm very curious, and this education system kills curious minds. It's not a silly question, it's a great question. It goes to the heart of what gravity is. So that's what we find everywhere we look. All planets that we know of are roughly spherical, whether these are rocky planets or gaseous planets like Jupiter, Saturn, etc. Even all of the moons, or most of the moons that we know in our solar system, are roughly spherical. The asteroids that we observe are of all shapes, right, and sizes. Most of them are not spherical, except the very largest asteroids like Eris, probably. There is this planetesimal or planetoid in the in orbit beyond Pluto. It's called Haumea, I think, which is oblong in shape. So it is not very large. And if we look around the universe, all stars are spherical. Our own star, the sun, is spherical. And exoplanets that we have discovered are also spherical. So what's the reason for this, right? That's the question. So the reason is gravity. Gravity is a force. So if you have an object, gravity is something that is concentrated in its center of mass. So every object has a center of mass, and the effective mass of that object is concentrated. It can be thought of as being concentrated in that center of mass. And the larger an object gets, the more powerful its self-gravitation is. And this gravity tries to create the most efficient shape possible by pulling all parts of the object towards the center. And the most efficient shape is a perfect sphere. Now, when an object is small, then its atomic structure, its molecular structure, the bonds within the molecules, etc., they overpower the force of gravity, and therefore it retains its shape. Right? So the everyday objects in our life, they have non-spherical shapes because the other forces overpower the force of gravity, which is the weakest force that we know of. But when you have an object that is large enough, around 1,000 kilometers or so in radius, then you find that the force of gravity eventually overcomes all of this. You will still have chunks of rock and all that. There are of all different shapes and sizes, but the overall shape of the object becomes more and more idealized. It tends towards becoming a proper sphere. That's because the mass essentially is concentrated in a way at the center of the object, in the center of mass, and everything is pulled towards that because of the force of gravity. That's why that's why it eventually, over time, especially if it's large enough, it slowly coalesces into a spherical shape. So that's very easy to see in gaseous planets like Jupiter, Saturn, Uranus, Neptune, etc. And even when you have rocky planets like the Earth and Venus, etc., because of the large size, the force of gravity overpowers the other forces and arranges the distribution of matter in a roughly spherical shape. So even today, the Earth is not perfectly spherical. It's like a squashed sphere. It has bulges, etc. But overall, from far, it does look more or less spherical. So that is the reason why planets are not triangular or rectangle. A planet has to be something that whose internal gravity forces it to assume a spherical shape. That's one of the definitions of a planet. So that's what it is. It's the effect of gravity that causes this spherical shape to emerge over time. Especially if the object is large enough, then it will very quickly become spherical. If it is smaller, then it may take some time. But today, the solar system is about 4.5 billion years old, so everything has become spherical. Whatever could, and that's the answer to your question. That's a good question. It's not a silly question. Akash asks, "What are solar sails? Can we build one in large enough to transport humans? And what are the speeds it can attain? And how will it help us once we get farther away from the sun?" So, a solar sail is a technology that could become a reality very soon. So it is essentially a very thin, very light sail-like structure, typically made of a very highly reflective material, metal usually, and it essentially works by the transfer of momentum from the electromagnetic field into the sail itself. So it basically gets a physical impulse from photons hitting it. So that's what a solar sail is. It works on the base because of radiation pressure. So radiation, like light, affects a physical pressure on objects, especially highly reflective objects, especially objects that are very light. So let me show you what a solar sail looks like. So this is an artist's depiction or representation of a solar sail. It's a very thin uh, structure, very light, and it's highly reflective. So there is a project being which is underway right now. It's called Breakthrough Star Shot. So this project uh, hopes to use this solar sail technology and send very small probes all the way to our nearest star, which is Alpha Centauri. And there is this exoplanet around this star system, which is called Proxima Centauri b. So this project hopes to send a large number of probes to this planet using this technology. So these will be very small probes, maybe a gram or two in size. These are like basically chips, computer chips, but they will have some instruments on them, very basic instruments, which would hopefully, once they reach there, be able to send us data or images back to Earth. So the technology is that we will have about 1,000 of these probes. Each solar sail will be a few meters across, and it will contain this little chip-sized nano satellite or nano probe of sorts. And these will be accelerated to about 15 to 20% of the speed of light using lasers. So either ground-based lasers or space-based lasers in orbit around the Earth will fire beams of laser light at these probes one by one, and within 5 to 10 minutes accelerate them to around 15 to 20% of the speed of light. And that's how these 1,000 or so probes will go all the way to that star system. Why 1,000? Because many of them could get destroyed or damaged on the way because of impacts with cosmic dust. So that's why 1,000 of these probes will be sufficient, hopefully, to reach there, at least a few of them in one piece, and send back some useful data to us. So this should be able to reach there, if we do it today, in about 20 to 30 years. And then another 4 or so years for us to get the signals back from there. So this is a technology that is almost possible. We need some improvements in our existing technology to make it possible, but it could be this project could actually take off in about a decade or so from today. So this is a technology that is very much feasible. It's only a decade or so away from today. We need to improve certain engineering and technological features, but it's very possible. Right now, we are in a position to send these very small, tiny probes to another star system. But in the future, as the technology improves, we could very well be possible. It could very well be possible to send human beings as well, which means basically you may have larger spacecraft which can hold humans or a number of humans, which could be transported on the basis of this solar sail or photon sail or light sail technology. So that's what a light sail is. It's a very interesting technology. It is very much feasible and it could happen soon. So it's one of the ways one could travel across space. It can it can transport payloads to a significant percentage of the speed of light, 10 to 15 to even 20% possibly. So that's the best we could have as of now, because chemical rockets can't attain such speeds. So this is the best technology, potential technology that we have as of today, that could enable us to cross interstellar space and reach another star system. So interesting, very interesting technology. Okay, Gaurav asks, what is the temperature of the moon and why does it fluctuate so much? So the temperature of the moon, like you said, it fluctuates a lot. When see the moon rotates around its axis once in about 27 days. So about 13 and a half days, each side of the moon is in sunlight, and about 13 and a half days, it is in the darkness. So the day is 13 and a half days long, and the night is 13 and a half Earth days long. So when sunlight is incident on the moon's surface, the temperature is about 123 or so degrees Celsius. And when the surface is in darkness, the temperature goes down to about minus 170 something degrees Celsius, 173 or 75 or thereabouts. So that's the kind of temperature range you have. And the moment sunlight it turns off, when the moon rotates and the sunlight is no longer available, then it almost immediately goes from 127 to minus 173 degrees, almost instantaneously. So why does this happen? It's because the moon has no real atmosphere whatsoever. On the Earth, we have this atmosphere which traps heat, and that's why you have a much milder change. That's why you have much milder and much gentler changes in temperature, the seasons, as well as day and night. You have only a few degrees of difference between day and night, typically. On the moon, it's a tremendous difference between day and night. It's because of the lack of any real atmosphere on the moon's surface. There is a very thin, tenuous atmosphere, a few atoms and molecules zipping around. The total mass of the atmosphere of the moon may be 10 metric tons or so. So it is extreme. It's basically negligible. You can regard it as a proper vacuum, the surface of the moon. So that is the reason why the changes in temperature are so drastic between day and night on the moon, because there is no atmosphere which traps heat. So that's the answer. Good question. Okay, Aditya asks a very good question. What is the theory of relativity? So the theory of relativity essentially is a theory of gravitation, a theory of gravity. So relativity came in two phases. In 1905, Albert Einstein put forth the special theory of relativity. And in a decade later, after a great deal of work, he put forth the general theory of relativity. So the general theory of relativity builds upon the very baby steps he took in the special theory of relativity. So I'll talk about the general theory of relativity, which is what relativity actually is. So until this theory came around, we understood gravity reasonably well. We had the Newtonian theory of gravity, which sees gravity as a force that acts at a distance, a force that acts at infinite distances instantaneously. So it's an instantaneous force. No matter how far you are from a massive object, you will feel its gravity. No matter how far you are, you'll feel it instantaneously. That is how Newton's law of gravitation works, if you can see the equation. So that is how we understood gravity. Now, general relativity says that gravity is not a force, it is the geometry of space itself. It is the curvature of space-time. Mass causes the fabric of space-time to curve, and this curvature is what we interpret as gravity, as this so-called, as this apparent force of gravity. So according to this theory, the entire fabric of the universe is a four-dimensional fabric. It's called space-time, three dimensions of space and one dimension of time, all integrated together. And that is what we are immersed in. That is the stage or the arena upon which the universe exists. So that's space-time. And everything in space-time has a limit, a speed limit, which is the speed of light. So that is something that's hard coded in the universe. Nothing can travel faster than the speed of light, not even these ripples in space-time themselves. Even these ripples in space-time will only travel at the speed of time, at the speed of light, I'm sorry, and not beyond that. So that is a very interesting effect. It's a very, very significant difference from what Newton said. So let me illustrate this by doing a thought experiment. So this here is a toy model of our solar system. We have the sun at the center and all the planets around it. The sun should be much smaller, but you get the point. So according to Newton's theory, this star at the center, right? The star at the center here, it exerts a force, an attractive force on all of the planets, and it's an instantaneous force. It's a force that acts all the way out to infinity. Now let's assume for a second that, let's do this thought experiment. Let's suddenly switch off the sun. The sun suddenly disappears all of a sudden for whatever reason. It's a thought experiment. We can do anything. So let's assume that I switch off the sun, I make it disappear. Then what happens? These planets are all going round, mostly round around the sun. And since the sun disappears, this force it was exerting on all the planets instantaneously disappears. And what will happen is all the planets will fly off in all directions, right? That's what will happen instantaneously. At the same time, all the planets will disappear, will go off in all different directions in various parts of space. That's what will happen according to the Newtonian theory of gravity. Now, according to Einstein's theory, general relativity, if the sun were to disappear, it would take 8 minutes for Earth to know about it, because the speed of light says that it takes about 8 minutes, roughly 8 minutes, for light from the sun to reach the Earth. So if the sun were to disappear, we would not know about it for 8 minutes. And it's only after 8 minutes that the gravitational effect or the sudden gravitational disappearance of the sun would have an impact on us. So it's only after 8 minutes that the Earth would fly off, and it would take longer for the other planets like Jupiter and Saturn to know about the fact that the sun has disappeared. And only then would they start flying off in different directions. So that is the difference, my friends, between Newtonian gravity and general relativity. General relativity, like I said, it treats the fabric of universe as a four-dimensional space-time, and this is the difference between general relativity and Newtonian gravity. General relativity is much more accurate than Newtonian gravity. We can still use Newtonian mechanics to send a rocket to the moon and bring it back safely. We can send people to the moon and bring them back safely without using general relativity, using just Newtonian mechanics. So it is pretty accurate. But there are certain phenomena that it can't account for. And that is where general relativity comes in. It is an improvement, a significant improvement on Newton's theory of gravitation. So that in very brief is what relativity is. It is a theory of gravitation. It is an improvement upon Newton's theory of gravity, and things such as GPS and much more would not have been possible had we not discovered general relativity. So that in brief is what it is. Good question, sir. Akash asks, do you think Dyson spheres are scientifically possible to build even if a civilization develops immensely? So there is definitely nothing in the laws of physics that would prevent a sufficiently advanced civilization from building a Dyson sphere. So let me show you what a Dyson sphere is. This is a hypothetical artist's representation of a Dyson sphere. It is a sphere that envelopes an entire star. It is a monumental piece of engineering. It is a sphere that envelopes an entire star. This thing will close around the star, and it will be basically be able to harness the entire energy output of that star. So that's what a Dyson sphere is. This is a hypothetical representation. This is another hypothetical representation of a Dyson swarm kind of structure being constructed around a star. So the objective of such a hypothetical structure is to harness the total energy output of a star. So you would need to be a very advanced civilization to be even able to think of constructing something like that. So it's a very you would need to be a very advanced civilization. There is nothing against the laws of nature, against the law in the laws of physics, that says we can't build it. But can a civilization reach that level of advancement? Well, we are nowhere near it. We are not nowhere near even being able to harness the total energy of our own planet. We can't control the weather, and there are so many things that we have no control over. We are trying to do it. We are doing a very bad job of it right now, but so we are very far from it. Is it possible theoretically? Certainly. So there was this thing in the news, a star that was exhibiting very erratic patterns of dimming and brightening. It's called Tabby's star. Tabby's star. Uh, I don't have it here open somewhere, but look it up. It's called Tabby's star. It's a star which is about a few hundred light years from the Earth, and it has this pattern or non-pattern of erratically brightening and dimming. The dimming affects about 27% of the light output of the star. So that is very considerable dimming. And as of today, we have no proper explanation of what could be the process that is causing this erratic dimming and brightening up of the star. So if there was some large planet or swarm of dust or swarm of comets orbiting the star, then this dimming and brightening would be periodic. It would be periodic, and we would be able to predict it. But in the case of the star, it is not predictable at all. In 2017 or 18, these events were very the brightening and dimming was very marked, very noticeable. Right now, it's not there much at all. So it is a very erratic pattern. And some people have hypothesized that somebody is building a Dyson sphere or Dyson swarm or Dyson ring around this particular star. And that possibility has not yet been ruled out, because there is no well accepted natural explanation of what's going on in the star. So that could be a possible candidate. There's a small chance it could be something like another civilization creating constructing something around the star. We don't have proof. It's a hypothetical possibility, but it is certainly a possibility that is being considered. So that's the deal. It could be possible, but we have never observed any real evidence. This is possible, tentative, perhaps evidence that perhaps something like that may be going on, but perhaps there is a natural explanation too that we are still not able to figure out. So yes, it is a possibility, but it is not anywhere near to possible for us, because we are still so underdeveloped technologically as a species. But theoretically, yes, definitely possible. Okay, loop quantum gravity for a dilettante. So that's a good question. What is loop quantum gravity? So loop quantum gravity is a quantum theory of gravitation. It's a quantum theory of space-time. So according to general relativity, like I said, space-time is this four-dimensional fabric inside which events occur. So it is the stage or the platform or the arena upon which various events occur in our universe. And even in string theory, the space is the background on which strings vibrate, one-dimensional strings. So this is a new theory. It says that the geometric fabric of space-time is not continuous. It is itself quantized. It is made up of discrete quanta of space-time, bits of space-time. So that's what loop quantum gravity says. And it says that distance itself has a minimum quantity, which is 10 raised to minus 33 centimeters. And this theory says that time itself is quantized. Time too has a minimum quantity, 10 raised to minus 43 seconds. And according to loop quantum gravity, LQG, the name suggests loops. So it says that space-time is made up of finite loops, extremely small loops. And the intersection of these loops is where these quantum uh, volumes of space reside. Each volume is 10 raised to minus 99 centimeters in size. It's a very, very, very small volume of space. So the intersection of these finite loops is where these quantum volumes of space reside. And in the terminology of this theory, large quantities of these loops of space-time are called spin networks. Spin networks. So space is defined by the geometry of these spin networks, of the spin network, and time is defined by the movements that rearrange the spin network. So time is an emergent property of the geometry of the spin network. It emerges when the spin network moves. And this spin network, when it is combined with the quantum movements, that is time. So the spin network, when combined with its movements, is called the spin foam. So time is quantized in the spin foam. It ticks like a clock, and each tick is 10 raised to minus 43 seconds long. And mass and energy distort shapes and volumes of the spin network. So this distorts space and time because any movement of these quanta also affects the time quanta. So time is the movements of this volume quanta, and the distortion of space and time is what we perceive as gravity. So that is LQG, loop quantum gravity. In a nutshell, it says the whole universe is a spin network. So LQG, loop quantum gravity, predicts a big bounce. It says that the universe will essentially bounce back if it contracts. Because, see, according to the Big Bang theory, what we have is that the universe is supposed to have originated as a zero-dimensional point-like structure, a singularity. And according to LQG, the smallest allowed volume of space is 10 raised to minus 99 cubic centimeters. So because of that, singularity is not possible, and therefore the universe in the future will contract again, and then it will bounce back and explode, so to say, or expand violently or very, very, very fast in an event that will look like a big bang. So it predicts a big bounce cosmology. So essentially, loop quantum gravity is able to, in a way, tell you what happened before the big bang. There was a big crunch, kind of a big collapse, a big crunch. So the previous universe, the previous incarnation of our universe, contracted upon itself after a period of time, and it went down to this minimum allowed quantum of volume, 10 raised to minus 99 cubic centimeters, and then it bounced back. So that's what LQG says. Is it proven? No, as of now, we don't have sufficient proof of it. It is a good theory. It is a theory that is taken seriously, and it needs to be refined further, and it needs to make predictions that are testable. As of now, we don't have any significant testable predictions, but it's a very good and very interesting theory. So that is loop quantum gravity in a nutshell. It's a great question. Okay, this is another great question. Do the laws of the universe also change with time? So, how do I interpret what you're asking? Basically, what you're asking is two different things. Firstly, do the equations of quantum mechanics and quantum field theory, and do the equations of general relativity, do these equations themselves change with time? So, that is part one of your question. And part two is, do the strengths of the forces of nature change with time? So we know about four forces of nature: the strong nuclear force, the weak nuclear force, electromagnetism, and the force of gravitation. These are four forces that we know of. There may be others that we don't know of. So do the strengths of these forces also change with time? So these are two questions you're asking. So as far as we know, the equations that govern quantum mechanics, quantum field theory, and the equations of general relativity, as far as we know, to the best of our knowledge, they do not appear to change with time. So to the best of our knowledge, no to that part of the question. Does the strength of the forces, do the strengths of the forces change with time? It appears that it does. So we know that it is known for a fact. I mean, it is known, strongly known, I would say, it's known that in the very so the best theory that we have tells us that in the very initial moments after the Big Bang, all four forces had the same strength, and then various forces decoupled. So that was the time when you had grand unification. All four forces were combined into one single unified force, and that is the grand unified theory that all physicists are seeking. That is the end point of physics, so to say, one equation that governs the entire universe. So so at the very beginning, in the very first moments after the Big Bang, it is believed that all four forces had the same strength. They were combined into one single unified force, and then the various forces decoupled, and they acquired different strengths. And gravitation, the force of gravity, is today the weakest force of all. It is many orders of magnitude weaker than the nearest comparable force. So that is what we know. So definitely we know that the strengths of the forces have changed since the initial moments after the Big Bang. Now, what is also known right now is that the strength of the electromagnetic force seems to be different, in very small amounts, in different parts of the universe. There is something called the fine structure constant. It is denoted by the letter alpha, the Greek letter alpha. So this fine structure constant quantifies the strength of the electromagnetic interaction. So it is essentially a measure of the strength of the electromagnetic force. And over the past decade or so, there have been hints, various observations, that the strength of the fine structure constant, which is the number, its value may be different to a very small degree in different parts of the universe. So it may kind of indicate that the laws of nature, the strengths of the forces may be different in different parts of the universe. It is a tentative finding. It is not yet 100% confirmed, but it does give telltale signs or indications that the universe may be stranger than we actually think it is. The laws, the forces that we experience here may not be the same forces you may experience in a very far off distant corner of the universe. Maybe there's a north and south to the universe itself with different strengths of the forces. So there is definitely very much a possibility, and it's a very intriguing possibility. So that would indicate that there is much more to the laws of nature than we understand. Maybe we have a very basic, rudimentary, surface level understanding of the laws of nature. So that's a very good question, and we need more data to uncover more about this. But yes, there is definitely data that seems to indicate that the strength, at least of the electromagnetic force, may vary. It may be different in different parts of the universe. Very interesting question. Akash again, the scientific community is divided on what the interstellar object Oumuamua was. What are my opinions about it? So, what is Oumuamua? It is an object that was discovered in late 2017, I think, October 2017. So, it's a very strange object. It was discovered when it had already crossed the sun. It had already gone around the sun. It was going away from the sun. So here's what this object looks like. It is an artist's depiction. It's an artist's representation. We don't have any real images of this thing, but we know its general size and shape. So it's about probably around 100 kilometers long. It is a thin structure. It's a cigar-shaped structure. And here's what we know about it. So we know its size, we know its rough shape, and we know that after it went round the sun, it was on a hyperbolic orbit, which means that it is going to escape the solar system. It's never coming back, which also means that it came from outside the solar system. It's an interstellar traveler. It's the first object we have discovered thus far, which is extra solar in origin. It is from interstellar space. It is not of our own solar system. So here's what we know about it. We know that it did not have any gaseous tail like a comet would have, right? And yet, when it passed the sun, it was going away from the sun, it actually accelerated. Now, we see this sort of thing quite often When you have a comet, it gives off gases when it is heated up by the sun's radiation, and this ejection of gases can cause comets to accelerate or decelerate, or it can cause their orbital paths to change. So it's very difficult to predict the exact orbit of a comet because of this reason. So you can maybe predict the orbit of a comet for 100 or 200 years at most, but then it's very, very hard to do that. So we found that this object, Oumuamua, exhibited acceleration, but it did not have any gaseous output. It did not have any coma. It did not have any cometary tail. So that is very perplexing. There is no mechanism that explains why this object accelerated away from the sun. Secondly, it is extremely highly reflective. It is at least 10 times more reflective than your typical solar system rocky object. So some people have hypothesized that it is a solar sail. So I discussed solar sails a couple of questions ago. So some people have hypothesized this could be a solar sail or a relic from some ancient civilization, something that was floating around in space at a very high velocity, and we happen to find it. So it is highly reflective. Maybe it's made of metal, and maybe it's a solar sail. Its shape is extremely atypical. Typically, you don't find objects of this shape, natural objects of this shape, in the solar system. It kind of reminds you of either a solar sail or a spent rocket part, like a booster of a rocket or something. So that's why some very respectable and serious physicists have propounded the hypothesis that this could have been our first contact with an extraterrestrial civilization. Now, this object is traveling very fast. It's already too far for us to really do any kind of observations. A radio telescope was pointed at this object for a few hours, but no signals were forthcoming. So it's a big mystery. But some very serious and very well-respected physicists have put forth the very serious hypothesis that this could have been our first encounter with an extraterrestrial civilization. I think it was Avi Loeb, who's an American Israeli physicist, who wrote a book about this even. So it's a very interesting phenomenon. It's a very interesting event, and unfortunately, we are not in a position to send any probe to meet up with this object, because it will take time to design and construct such a thing, by which time this thing will be gone. So from what data we don't have the answer, a very definitive answer, but yes, it is very intriguing, and it could have been something possibly from somewhere else, something that was created by intelligent beings, perhaps. So the possibility is there. I do take this possibility seriously, but we don't know for sure. So that is where we are at with this question. Siddhant asks, can a person study astrophysics or advanced physics if he or she doesn't know complex mathematics or doesn't have a mathematical background? Unfortunately, no. Short answer, no. You cannot study advanced physics of any kind, any field, without a thorough understanding of mathematics. This is the basic prerequisite for studying physics. You need to put in the hours and the days and the weeks and the months and the years studying mathematics of ever increasing complexity. So that's what physicists have to go through. That's the price for admission for being a physicist. You have to study all kinds of math. Basically, it is calculus, differential equations, linear algebra, matrices, vectors, and various other things. You can just purchase a book on mathematical methods of physics, but you have to start at the very basic level: school, high school, college level, university level, etc. So unfortunately, you cannot really study physics or do research in physics or comprehend real physics unless you put in the time and pay your dues and learn the math. Otherwise, you just have to rely on other people to give you information about physics, like what I am doing right now, or your favorite personal astronomer or astrophysicist. So that's the deal about physics. You really need to know the math in order to properly comprehend it and to come to your own conclusions about it, instead of relying on basically the opinions or the facts or ideas given by others to you. So you do have to learn mathematics, and the mathematics can get really complex at times, especially when you are dealing with string theory or even general relativity, when you have tensor calculus, etc. So that is a basic prerequisite for doing real physics. Yes. All right. This is the last question I've selected thus far. Yash asks, please explain Hawking radiation and how will a black hole vanish after trillion, etc. years? So Hawking radiation is a very interesting effect. So what we know about black holes is this: a black hole is essentially an object whose that is so massive and so compact and so dense that even light cannot escape from it. Not even light can escape from it, which means that it can absorb mass and energy. What this indicates is that an object from which nothing escapes, but an object which will swallow or eat up or absorb mass and energy, which means that an object like this should only be capable of growing larger. It should never be something that can decrease in size. That is our understanding of black holes. That's what general relativity tells us. Now, what Stephen Hawking found, I think he had visited the Soviet Union, and a couple of Soviet scientists told him that black holes, especially rotating black holes, should be capable of emitting radiation. So Stephen Hawking applied quantum field theory to the edge of black holes, to the space time that is around the event horizon of black holes. And what he found was that black holes do emit radiation. So here's one way of looking at it. Let's say I have a black hole, okay, a spherical object, and let's say this is the event horizon here, and the black hole center is here. Now we know from quantum field theory says that the entire vacuum of the universe is made up of fields of various various kinds, and there is this vacuum energy in there. So the vacuum of space is teeming with these virtual particles. Particle-antiparticle pairs are constantly being created and annihilated in accordance with Heisenberg's uncertainty principle. So this particle antiparticle pair appears and annihilates very quickly, very rapidly, so quickly that it does not violate the time component of Heisenberg's uncertainty principle. So the entire vacuum of space is actually teeming with these particle antiparticle pairs, and we have experimental confirmation of this Casimir effect. So what we know is that you have this in empty space. Now, at the edge of a black hole, at the edge of the event horizon, let's say a particle antiparticle pair is formed. Now, the energy is borrowed from space-time itself, and when they annihilate each other, the energy is given back to space-time. So the net change in energy is zero. Let's say a particle antiparticle pair is formed right outside the event horizon of a black hole, and it goes into different directions, and before it can recombine, one of the particles or antiparticle is absorbed by the black hole because it crosses the event horizon, and the other one is then free to go away, which means that from a virtual particle it became a real particle. Right now, the energy was borrowed from space, from space-time, from the vacuum of space. It was supposed to be given back to the vacuum of space. Now what happened is that one particle went inside the black hole, and the other particle is now available to us. So we have gained the energy of this particle, which effectively means that to compensate for this energy we gained in violation of Heisenberg's uncertainty principle, it means that the particle that went inside the black hole has negative energy or mass, which means the black hole actually shrinks by a little bit when this happens. And that is the process. That is one way of looking at Hawking radiation. The actual manner is different. This is a good analogy of how this thing happens. So because of the creation and annihilation of particles in space-time, when it happens at the edge of the event horizon of a black hole, you have these particles that escape from it, and which we see as a flux of energy and radiation actually. And what goes inside the black hole has negative mass. So over time, the black hole slowly over time shrinks. So for somebody who is standing or sitting far away and observing a black hole, it looks like the black hole is radiating energy. It is radiating particles. It is radiating. It is emitting radiation, and it is this radiation that's called Hawking radiation. This is called black body radiation. Okay, that is a term that you can look up. So an object like a black hole actually emits radiation, and we know that anything that emits radiation has a temperature. So black holes have temperature. The larger a black hole, the colder it is. The smaller a black hole, the more radiative it is and the hotter it is. So the thing is, the smaller a black hole, the more radiation it emits, and the faster it emits radiation, and the hotter it is. And therefore it gets smaller quicker. So small black holes shrink faster and faster until at the very end it explodes in a burst of Hawking radiation. So that is Hawking radiation. That's what it is. Black holes, even though they are dark, even though they are black, they still do emit Hawking radiation by this semi-classical theory of Stephen Hawking. Have you ever observed Hawking radiation? Thus far, we don't have any real evidence of it. But theoretically, this is what happens. So that is the answer to your question. So how long will a black hole last? Large black holes, they have lifetimes that exceed the current age of the universe. So they could be around forever. And they are so cold that instead of emitting radiation, they absorb the cosmic microwave background radiation, and then they grow larger. So black holes beyond a certain size, they are most likely essentially immortal black holes. They will live as long as the universe exists. Smaller black holes have a finite lifetime. They emit radiation, and so you can calculate what exactly the temperature and the lifetime of a black hole is. There's a formula for that. So certain black holes are de facto immortal, and some smaller black holes will eventually meet their fiery, explosive demise. So that, sir, in brief, is what Hawking radiation is. Now let me take a couple of live chat questions. Let me see what you have. Lots and lots. Okay. Narhari Rao, thank you for the super chat. Roger Penrose's conformal cyclical cosmology talks about eons, where the end of every eon is also the beginning of another eon. Sounds eerily similar to Kalpa's. Can I elaborate? I haven't really studied his theory in detail. I think he's written a couple of books about it and some papers. What I understand is that the universe keeps expanding and expanding until it is almost completely empty, and then you can transform the equations of space-time, etc., in such a way that it resembles a new Big Bang of sorts. So that's what it seems to be. I personally haven't studied this particular specific theory. It's an interesting theory. It is definitely a valid theory of cosmology. So that's what he calls eons. The universe is a very long lifetime, after which it re-emerges as a new universe, as a new Big Bang. So that's what he calls eons. I'm not sure if it is the same thing as the kalpas. Kalpas are... I am not very clear about the terminology of kalpas, so I am not sure whether it is the same thing as that or whether it is similar to that. Maybe what I'll do is I will look up what exactly kalpas are, what the terminology means, and then maybe I can revisit this question. And I can also look up Roger Penrose's theory, conformal cyclical cosmology. So it is essentially the theory of a cyclical universe. There are many other such models. There is also, like I said, the big bounce model in loop quantum gravity. So these are similar models which say that the universe won't expand forever, but there will be cycles of big bangs and maybe big crunches or big bounces and various other iterations similar to that. So it's essentially a cyclical model of the universe. And it, in a way, is similar to ancient Hindu cosmology, which also says that the universe has cycles. Each universe has a Brahma associated with it, and each Brahma has a finite lifespan. It's a very long lifespan, maybe in the trillions of years, if I'm not mistaken. But it does end. So it's a cyclical cosmology, which is what our ancient forebears thought about and came up with. So if that is what you mean by kalpas, then yeah, it is similar to that. So I will just reconfirm what these terminologies mean, and then maybe I can answer it again in a future episode. So thank you for the question. Okay, I'll take a couple more questions. Ashish asks, what's possible relevance of the asteroid belt versus with respect to chances of asteroid excavation in the coming future? How far is it? Well, if we can get to Mars, then the asteroid belt is just a hop and a skip away from there. It's not really very far from there. So the asteroid belt, like most of us would know, it lies between the orbits of Mars and Jupiter. It is most likely the remnants of a destroyed planet. Maybe there was a planetary collision in the infancy of our solar system, and this the material of this planet was scattered all over, and it remains in orbit. And that's what the asteroid belt is. It's a bunch of rocks, space rocks, and it is known that some of these rocks are metallic, very metallic. They contain great deals of great quantities of various metals. Some of these space rocks may have more metal than all the metal that we have on Earth itself. So yes, it is a very lucrative future in industry, asteroid mining, asteroid excavation. If we can develop the technology to get there, maybe we can even tug an asteroid into Earth's orbit or something like that, possibly, and extract various metals, minerals, and other resources from it. And so that would be the next big thing in industry, in mining. It could create trillionaires out of people, or corporations. So it will most likely happen maybe in the next 50 to 100 years. Maybe it will most likely start in that time period, because we will most likely send humans to Mars in the 2030s, if not before that. I think most likely in the 2030s. We are returning to the moon in just a few years, within the next 2, 3 to 5 years. So the Americans are planning to send humans to the moon. The Chinese have plans, and the Chinese are tying up with the Russians. Maybe the Russians will also be involved. Now we have these plans with SpaceX to send people to Mars by the 2030s, definitely within the 2030s. So the next logical step would be to explore asteroids. So I think that we could start doing this by the 2030s or by the 2040s. Definitely, the beginning will be by 2050, before 2050. But it will become it takes time for an industry to grow and mature and to reach a stage where it is commercially viable. So I think definitely within this century sometime we could have proper commercial asteroid mining. So it's definitely there in the future, no doubt about it. But it's not something that we will see in the next 10, 20 years. But definitely within the century for sure. Okay, one more question. All right. Do you think the future has Rahul Raghunath asks this. Do you think the future has an effect on the past? Just like the past has an immediate effect on the present and future, Einstein's block universe explores this. Einstein gave us the theory of relativity. I don't know what block universe is. Maybe it's a colloquial way of referring to something. I am not familiar with this term block universe. The theory he gave us was general relativity. In general relativity, you have causality. You have the possibility of wormholes, which could possibly enable you to travel back in time. It is a possibility. We don't know yet if it is feasible, and maybe there are laws in the universe that prevent such time travel from happening so as to preserve the laws of causality. Quantum mechanics tells us that there may be no past, present, or future. There may be no causality at all. So these are all hypothetical concepts right now. We don't know because we don't understand quantum mechanics. We know how to use it. We know how to use the equations. We know how to solve problems. We know how to create technology with quantum mechanics, but we don't know what quantum mechanics is telling us. We don't know what it is at its very core, at its very fundamental level. So the universe is a very big mystery right now. We don't know if time is an emergent property. Loop quantum gravity says that time is an emergent property of the geometry and the motion of the loops of space-time. So this is all out there in the open right now. We don't have any definitive answers to the question of past, present, future, the question of what time is, time itself is, and to the question of whether causality is even a thing or not. So these are the boundaries of reality that we are exploring. This is why theoretical physics is so fascinating, because there is so much that we don't know, and that's why we are looking into these things. So that's my answer. I don't have a definitive answer for you. Physics does not, as of today, have any answers, and that's what makes it so interesting. All right, my friends, I am done with today. We have come to the end of today's episode. Thank you very much for your wonderful, fascinating questions. Keep asking me. We're going to have another session next week, and we're going to keep doing this. So thank you so much. Thank you so much. I love the questions you've asked, and I will see you in tomorrow's episode. Thank you. Have a good day. Have a good night, and I'll see you in the next episode. Bye.